Okay, welcome everyone. Thank you for joining us today for today's webinar, AI-driven forecasting, fact or fiction. My name is Dinesh Shah, and I am the founder of Supply Chain Business Solutions, based in Sydney, Australia. Our partnership with Business Forecast Systems goes back to year 2000, and today we have partnered with them to bring this important webinar, very relevant to the digital era we all live in. We'll begin the webinar shortly, but let's go over a few logistics. The webinar presentation will run approximately 55 minutes, and we will save the time at the end for Q&A. During the webinar, you can submit questions using a Q&A function on your screen at any time, so submit them as they occur to you. We're monitoring these questions throughout the webinar, and we'll compile a list for the Q&A at the end of the presentation. We'll also take questions submitted during the Q&A session itself. We'll do our best to address as many questions as possible. If you do not get to your question, you will receive a follow-up email after the conclusion of the webinar. We will also be recording this webinar, and we'll email you a link to the video sometime next week when it is available. The webinar will also be posted on the Forecast Pro website and Forecast Pro YouTube channel, where you can find full archive of past webinars. They are free and a great way to catch up on any past webinars you may have missed. Now I will hand over to Sarah Darin. She is the presenter for today, to introduce herself and kick off today's webinar, AI-driven forecasting, fact or fiction.
Thank you, Dinesh. I'm Sarah Darin, and I am a mathematician and statistician, basically. I spent a lot of my career doing actually analytical consulting, and that was mostly creating sales regression models, so models that would explain and forecast sales for lots and lots of different companies. I joined BFS, BFS/Forecast Pro, about 8 years ago now, almost 8 years ago. And my role at BFS is really, I lead analytics, data science, which made me basically the architect of machine learning and how we wanted to design and implement it in Forecast Pro. So I had a chance to go over and learn a lot about machine learning in particular as I embarked on that. So thank you again, Dinesh. We really appreciate your partnership, and we hope that everyone enjoys the webinar. AI has truly emerged as a transformational field that touches everybody. AI has allowed things like facial recognition, language processing, self-driving cars become a reality. And we've seen ChatGPT become an integral part of daily life for many. AI is so pervasive now that governments are very actively pursuing legislation on how to make sure that it's not used for nefarious purposes, something I am strongly in support of. AI is a term that really everybody knows at this point, and a lot of people understand the general framework, but the same is not really true for machine learning. Many people have heard of machine learning and realize that it's related to AI, but that's really about it. So I decided we should start off with a good, succinct explanation of machine learning and how it relates to AI. So naturally, I looked to AI to help me out. I asked ChatGPT this question here: what is the difference between AI and machine learning? I was using the microphone on my phone at the time, so what my phone first heard was actually, what is the difference between an eye and machine learning? The first application of AI by ChatGPT was to translate my question to the one that I intended to ask. And the answer that I got back to this question was not exactly succinct. It was 3 paragraphs long, but this last paragraph did capture the essence of the difference. In summary, AI is the overarching concept of creating intelligent systems, while machine learning is a specific approach within AI that involves training models to learn patterns from data and make informed decisions. Basically, ML is a subset of AI, and essentially ML-driven forecasting is a more specific term than AI-driven forecasting. But given that AI-driven forecasting may resonate more with the general population, it's quite reasonable to use that term instead. Essentially, it's probably just fine to use machine learning and AI-driven forecasting pretty much interchangeably. While ChatGPT gave us a good general overview of ML, let's dive into this question a bit more, perhaps with a bit more of a verified source. So, what is machine learning? Machine learning isn't just one approach or method. It encompasses a wide range of algorithms and approaches. What these algorithms have in common is that they are designed to find and apply patterns in data. These methods can be broadly described in 2 categories: unsupervised and supervised. Unsupervised machine learning uses what we call unlabeled data to find patterns or associations in the data. Unsupervised machine learning is good for things like speech and facial recognition, market segmentation, things where you're trying to put data into like groups. Supervised machine learning uses labeled data, and it is actually used for prediction. Where does demand forecasting fit in? Forecasting is prediction, so we know that we want to use a supervised machine learning algorithm for demand forecasting. Let's take a closer look at the differences between unsupervised and supervised machine learning. Let's start with an example of how unsupervised machine learning works. So suppose your data includes images of different fruits, maybe apples and bananas. An unsupervised machine learning algorithm would analyze those images and identify that there are 2 different types of images and basically separate the apples from the bananas, but without knowing if each image is an apple or a banana, because we haven't told the algorithm that this is an apple and this is a banana. So the algorithm is unable to predict if a new image, an unseen image so far, is an apple or a banana. It can simply identify which of these 2 groups that new image belongs to. In a supervised machine learning algorithm, each image would actually be labeled as an apple or a banana. In this case, we're really calling this whole input data set the training data. Instead of just separating the apples from the bananas, the supervised machine learning algorithm would learn how apple images are different from bananas and be able to identify a new image specifically as an apple or a banana. So we send the training data into a machine learning algorithm, we train a model, and then as new data comes in, as test data comes in, so new images, we're able to say that this is an apple and this is a banana. Again, because we're predicting and forecasting is a type of prediction, it really requires a supervised machine learning algorithm. So how do supervised machine learning algorithms work? Let's start by talking about a little terminology. If you hear data scientists talk about machine learning, you're likely to hear them talk about features and labels. Features are like explanatory variables in a regression model. Labels are like the dependent variable. So labels are basically what you're trying to predict or forecast. A machine learning algorithm might be able to automatically create features from an image, and a lot of people do try to do that with machine learning algorithms. But more often than not, data scientists actually really need to transform the raw input data into organized features themselves. So that's what we have here. We have taken those images of bananas and apples and created features that describe those images. So they capture a lot of the characteristics of those images, and then we have some labels. And this, of course, is the fruit type that we are actually trying to predict. So we're telling the algorithm exactly what each image is. So over here we have our features, for example, color, length, and shape, describing the images, and then we label those features with what type of fruit each is. This process of organizing the raw input data into features and labels is called feature engineering. Good machine learning models start with good feature engineering, and that means data scientists end up spending a lot of their time, a majority of their time actually, 60%, cleaning and organizing the data. So essentially doing all that feature engineering. As we embarked on implementing machine learning in Forecast Pro, understanding how we could actually automate feature engineering was really a key part of the research and implementation process. If you think about it more broadly, machine learning models have primarily been a tool for data scientists. Many companies have big teams, huge teams sometimes, of data scientists who are deeply involved in custom coding in Python or R, these machine learning models. And they really need a solid understanding of both how feature engineering and machine learning work in order to generate these models, of course. Our goal in implementing machine learning in Forecast Pro was to basically take the data scientists out of the equation. We wanted to give Forecast Pro users the ability to use machine learning models for demand forecasting without having to worry about coding, feature engineering, or model refining. If you want to learn more about the details of how we automated machine learning in Forecast Pro, we delve into those details in our methodology workshop, an online workshop that we offer a few times a year, and actually we plan to start having some more in-person ones next year as well. But for this webinar, let's focus more on when should I use machine learning. So let's take a look at machine learning in Forecast Pro. When we first implemented machine learning, first and foremost, we wanted to make sure that machine learning could be used in an automated way, that you didn't need to be a data scientist to use it. And that's why, as we mentioned earlier, we automated feature generation from historic demand. So it is a univariate method. As an automated univariate method, that meant that it could potentially be also included in expert selection. For anyone not familiar with expert selection, it is our AI-driven automatic forecasting algorithm that really has always been the workhorse or brains of Forecast Pro since we released our first version almost 30 years ago now. So we actually really were on the forefront of AI technology 30 years ago. But just like people adapt, grow, learn, and get better over time, so has Forecast Pro's expert selection. So we do keep changing it, as we see fit and where we see potential for improvement. Essentially, expert selection automatically selects the best forecasting methodology for your data. In order for us to include machine learning in expert selection, we really need to convince ourselves that it would be adding value. Expert selection is a really big part of the identity of Forecast Pro, and making sure that it truly was using the best methodology was kind of a cornerstone that we really needed to maintain. So we did some research, and essentially we determined that machine learning should be used for some data series often enough that it definitely made sense to include machine learning in expert selection. And you'll see that when we read in some data here and read in our bakery data, a data set that I suspect many of you may be familiar with, when I hit this read and forecast button here, Forecast Pro is going to automatically use machine learning to forecast all of the series and data that we've just read in. So what we're looking at here, our bakery data, has cakes and muffins, and that breaks down into customers and then further into SKUs. Now I'm going to go ahead and close our override grid here and go to our reports tab and open up the item report. And what I can do in the item report here is, if you look through this, you can see that we have all of our items and we list the model family for each of the items. And you can see machine learning coming up quite a bit. But what I'm going to do is I'm going to put on some filters here, and I'm going to select all of the items that selected machine learning, and I'm going to add them to the hot list. And I'm going to expand this up over here a little bit. So you can see here there are quite a few series where we end up using machine learning. So expert selection is selecting it as the best forecasting methodology for these series. You can see that muffins is coming up a bit more than cakes. But let's actually take look at some of the details of these machine learning models. So I'm going to close the item report. I'm going to add in the forecast report, and I'm going to add in fitted values. So let's just take a look at how it's fitting across some of these series. You can see actually the fit is quite good for some. Let's actually take a look at this here. And again, the reason I can tell that the fit is good is that this red line, so the historic fitted values, is actually trending relatively closely to the green line, the history for a lot of these series. And this forecast in particular here is looking pretty reasonable. The reason why we're selecting machine learning, though, isn't so much about how well it's fitting historically. It's more about how well it forecasts. And that's really the criteria that we're using for selecting machine learning. So machine learning is forecasting out of sample better, and that's why we end up using it. Let's actually scroll down to more details here, and you can see some terms like tree depth used, number of trees. We'll talk about the details of that pretty shortly. But for now, let's actually focus more on what features we're using. So here for carrot cakes, we have seasonal period listed first, and that's going to be what month it is. We have one period lag, so what were sales last month. Interventions. Interventions are a way for the model to automatically detect shifts in the data, spikes in the data. So if you have very noisy data, you're likely to see interventions coming into play in these models. Seasonal lag, what were sales last year, and then 1 year moving average. So these are the features, and they're ordered in this way for carrot cakes. And as we go through here, you'll see that the order actually changes a bit for each of these series. And we'll talk about why we're ordering them differently for each series in a bit as well. The main thing is the highest you are on this list of features, the more important that feature is for the forecast. When we read in this data, you probably noticed that there was a little dialogue that popped up that was telling us how many series have been forecasted, and it said that machine learning is enabled. Why do we have that dialogue? One of the things about machine learning is that it can take a long time. That's because machine learning is essentially analyzing the data and creating multiple models. So each model that the algorithm creates, it then learns from the previous, it's learning from the previous model really to figure out what the best model is. If longer forecasting times are a concern to you, or after this presentation you don't think that ML should be used for your data, you can actually disable machine learning by going to Options and then going to the Performance tab here and selecting Exclude Machine Learning. So I'm actually going to go ahead and do that, and you can see what happens. So it says we're going to reforecast. It actually is happening quite quickly. And you can see now for chocolate layer cake, instead of the machine learning model, we have an exponential smoothing model. We include machine learning in expert selection by default because it does improve accuracy for many series, and many demand forecasters don't have the bandwidth to decide which series should use machine learning. That said, if we do disable machine learning in expert selection, you still have the ability to use automatic machine learning models wherever you might see fit. So what I could do is I could disable machine learning and expert selection, but if I think that machine learning might be good for chocolate layer cakes, I can select machine learning, and with a click of a button, I can apply that same machine learning model that expert selection had selected before. And we can do that, of course, for any of these other ones as well. What if we actually wanted to use machine learning and expert selection just for a few select series as well? We can do that too. We can go with the drop down here and we can select expert with machine learning. And now you can see, instead of just applying that automatic machine learning model, we're actually using expert selection, and again, machine learning is coming out as the winner in that expert analysis. It also might be the case that you only want to use machine learning, for example, in one level of your hierarchy. So instead of using machine learning for all levels here, suppose I just want to be using it for the end items. I could go ahead and do that, and I'll apply this to this level. And you can see we're forecasting again with machine learning enabled for just those items. By disabling machine learning in those options, you can then manage where it's used in expert selection or as an automatic model yourself. Let's actually go back to the slides now to get more details about the Forecast Pro implementation of machine learning. Setting up features and labels is required for pretty much all supervised machine learning algorithms. But once you have it set up, there are a lot of different machine learning algorithms to consider. So things like neural networks, deep neural networks, support vector machines, random forests, the list goes on and on. And as you saw, at least suggested in the forecast report, we ended up choosing something a little different from this. We implemented extreme gradient boosted regression trees. Why did we do that? It's because we wanted to start by implementing a methodology that has been proven to forecast well. And extreme gradient boosted trees have performed very well in recent forecasting competitions, particularly the Macrodacus competitions. And those of you who are familiar with the Macrodacus competitions know that they're really considered to be essentially the gold standard of forecasting competitions. So the fact that extreme gradient boosting worked so well in those competitions really held a lot of weight with us at BFS. Let's take a look at how a regression tree works with a very simple example. Here we have a very simple tree and it's using two features. So we have month and we have sales last year. So we're generating a forecast value based on the values for these two features. How do we do that? Well, let's take a look at some examples. Suppose we're forecasting September 2023 and sales in September 2022 were 350. We start at the top of the tree and we ask, is the month November or December? So is the month greater than or equal to 11? The answer to that question is no. And that takes us to another node and another question. Were sales last year greater than or equal to 400? And again, the answer to that is no. And that takes us to a final forecast of 300. Let's take a look at another example quickly. So now let's suppose that we're forecasting for October 2023 and sales in October 2022 were 450. Again, October is not November or December, so the answer to the first question is no. But now sales last year were 450, so the answer to this next question, were sales last year greater than or equal to 400, is now yes. And that takes us to a forecast value for October of 550. A few other terminologies that might be useful coming from a regression tree include things like tree depth. What is tree depth? You saw it on the Forecast Pro forecast report. Tree depth is the length of the longest path from the top of the tree to the bottom of the tree. So in this case, that's the number of arrows going from the top to the bottom, and the longest path is going to be equal to 2. The higher the tree depth, the more complicated the tree. And we'll talk about this a little bit more later, but the general idea of training a model is you want to make it as simple as possible while still forecasting well. So keeping down the complexity is generally going to be a good thing. Some other terms that you might see, not so much in the forecast reports, but a bit in machine learning literature, is split nodes and leaf nodes. Split nodes, the blue ones, are also called decision nodes. These are where you have a question and you're moving on to another node. The leaf nodes or terminal nodes are the ones that are going to have the final forecast values. So what are extreme gradient boosted trees? Regression trees are essentially the building blocks for extreme gradient boosting. That's because extreme gradient boosting is an ensemble method, which means that we're taking the average forecast across multiple models. Ensemble methods have generally performed well in forecasting competitions, such as the Macrodacus competitions, particularly for automatic forecasting. The models that we're averaging across are regression trees, and extreme gradient boosting really focuses on finding simple trees in order to avoid overfitting, which we'll talk about in just a minute. But avoiding overfitting is really important for forecasting and really modeling in general. If we think back to the data scientist slide and how they spend their time, feature generation was a huge part of it, 60%, and we have automated that. But another part is figuring out the right parameters, tuning the model. For extreme gradient boosted trees, the two most important parameters are maximum tree depth, so how complex can each tree be, and the number of trees, or the number of models you're averaging across. Using trees that are too complex or using too many trees can easily lead to what is called overfitting. Overfitting means that your model fits your data well historically, but it doesn't forecast well. In order to automate extreme gradient boosting, we needed to automate how to identify the tree depth and number of trees that forecast most accurately. So we did that using very similar AI-driven techniques to those that power expert selection. We're not going to get into the details of how we optimize gradient boosted regression in this webinar, but if you are interested, we do review those details in our methodology workshop. Let's go back to Forecast Pro and take another look at the forecast report. So here we are back in Forecast Pro, and what we're looking at here is carrot cakes. Let's look at more closely at some of the model details in the forecast report. So Forecast Pro for carrot cakes generated a automatic machine learning model that has a maximum tree depth of 2, and it's averaging across 14 different regression trees. So this is a pretty simple model. If we choose a different series here, we'll see that there's a different number of regression trees being selected. Tree depth is actually the same, although if we go to yet another series here, so another chocolate cake series, we can now see that a tree depth of 3 is being selected, and the number of regression trees is 139. The point is that Forecast Pro is automatically detecting, using its AI-driven technology, it is optimizing the tree depth and the number of trees to use for each individual series. The other thing that we already mentioned varies from one series to the next is the order in which we are listing these features. The way we're listing these features is by importance. So the most important features are listed at the top, the least important at the bottom. So in this case, seasonal lag, what sales were last year in the same period, is the most important feature. And that again is going to change from one item to the next. This next item here, it's actually what sales were last month is the most important feature. How are we determining importance? For this webinar, we're not really going to get into that too much. If you want to have a better understanding of how we're measuring importance, again, we recommend that you consider taking our methodology workshop to get more details on that. Automatic forecasting is really a workhorse of the forecasting process. Typically, you start with automatic forecasting and then identify which series need more customization. Sometimes the customization includes just changing the univariate method used, but more frequently there's other information, things like promotions, price changes, or stockouts that you want to incorporate into your forecasts. One of the strengths of machine learning is that it allows you to include features that incorporate domain knowledge, things like price changes, the weather, and the economy. While Forecast Pro machine learning algorithms automatically generate features for univariate forecasting based on the historic demand, it's not going to be able to automatically generate features to capture your domain knowledge because it simply doesn't have access to your domain knowledge. You need to tell it. So in order to integrate your domain knowledge, we created what we call custom machine learning models. Custom machine learning models allow you to include things like events and explanatory variables in your machine learning models. The idea is these events and explanatory variables are a way that you can read in your domain knowledge into Forecast Pro, and then Forecast Pro is able to use these variables, these features, to forecast, to include in your custom machine learning model. So let's actually take a look at how custom machine learning models work in Forecast Pro. So we're moving on now from bakery data to mouthwash data. So this is another data set that's installed with Forecast Pro. So if you do have Forecast Pro installed, it's available to you. And it includes 2 SKUs of Minty Fresh mouthwash. And we've also gone ahead and read in a couple of helpers, so event schedules that integrate some domain knowledge about this mouthwash that we'll get to shortly. But before we do that, let's actually take a look at the historic demand for the 24-ounce bottle. If we look at these spikes here, and these spikes really are what catch your eye when you look at the data, let's take a look at when they're happening. This first one is in May, then October, then January, May, October, January, July, October, January, July, October, January. So we're seeing that there's a shift when these spikes occur. So this is an example where you really want to be thinking about domain knowledge. Why are we seeing these spikes? Is mouthwash seasonal? No. The use of mouthwash is probably pretty consistent throughout the year. It turns out that these spikes are actually driven by price specials. And that is why we have called our event variable over here price specials. If we take a look at that event variable, we can see that these price specials are pretty well aligned with when we saw those spikes. So we have October, May, and January coming up, and then even we see the shift happening in this event variable as well. This is a good example of data where in order to generate a good forecast, we really need to account for when these price specials are happening. So I'm actually going to go ahead and go back to our SKU here, and I'm going to put in the forecast now. What you can see is that we're not really seeing the spikes in the forecast horizon. There's some movement up and down, but not a whole lot. The model we've selected, we can see, is a machine learning model. And even though we actually see seasonal lag as a pretty important feature, when we look at the forecast, it actually looks a little bit like the model is learning that the spikes aren't really seasonal. But in the absence of other information, such as the price specials variable, the spikes are attributed a little bit to seasonality and a little bit to noise. If we look at an exponential smoothing model instead, you can see now the exponential smoothing model really is considering these spikes to be seasonal, and we see that in the forecast horizon. Bottom line, though, is both of these models, both the exponential smoothing model and the machine learning model, are generating bad forecasts. In order to generate a good forecast, we really need to account for when these price specials are occurring. So we need to incorporate our domain knowledge about when the price specials occurred in the past and when they're occurring in the future into our forecast. Let's go ahead and do that. Let's start actually by trying out an event model. So I am going to go ahead and I am actually going to build an event model with just this price specials event. And what you can see now is in the forecast horizon, we do have spikes happening the 2 times when we have price specials occurring during the forecast horizon, but we can also see that the forecast is pretty flat between when those price specials are happening. So let's take a look at what happens with machine learning. So I'm going to come over here and select my custom machine learning model. And when you see this, you can see that we have the ability to name various models. We also see sections for specifying events and explanatory variables. We don't have any explanatory variables read in right now, so this box is empty. So what I'm going to do is I'm going to select price specials. I am going to go ahead and use automatic for helping us determine the right number of trees and the right maximum tree depth for our models to use. And I'm going to go ahead and hit apply. When I do that, you can see the forecast shift a bit. In particular, what you can see is we still have these spikes happening when the price specials happen, but we also see these dips happening after the price special. Why is that? The machine learning algorithm is basically learning that after a price special happens, you very often are seeing a dip in demand right after that promotion. And that's actually pretty common after you have a promotion. People are going to move up their purchasing of something, and that causes post-promotional dips. The machine learning algorithm is figuring that out on its own. So we're not telling the machine learning model to look for that dip, but it is in fact finding it without our having to do so. So you can see here that in the forecast report, price specials are actually the most important feature, and the percentage of the model accuracy being contributed to by price specials is particularly high at 91%. I'm actually going to go back to our custom model here. An advantage of machine learning models using events is that you can actually use multiple events. That's something that you can't actually do with event models. For machine learning, you can select however many schedules you might want, however many explanatory variables you want. When the machine learning algorithm runs, it's actually going to only use the variables that are going to help improve forecasting. So as an example of that, let's actually take a look at this schedule 01. So I'm going to actually cancel out of here, and let's take a look at this schedule. What this is basically is it is an event schedule that has a single event happening on April 2020. And I'm calling this a non-event because if we look at April 2020 in here, it's actually right here, nothing really happened in there. So including an event schedule with a single spike there should not be an important driver for the Minty Fresh mouthwash sales. So let's see what happens when we add this into our custom machine learning model. So let's go back here, and we now are selecting the schedule 01, and let's go ahead and hit OK. The forecast didn't change, and the model didn't change. The schedule 01, the non-event, is not even being used by the machine learning algorithm. It is not included in our final machine learning model. The machine learning is actually doing a good job of model specification and only using the variables that actually make a difference to our mouthwash demand. That's great, but there are also some drawbacks to using event schedules in machine learning models instead of event models as well. When we look here, we can see price specials are indeed a really important feature, but we don't really see what the impact of the promotions are on demand per se. If I switch this over to an event model now, we can see exactly what the impact of the promotion is. We see an index of 2.169 right here, meaning that when a promotion happens, we see sales a little bit more than double. And that's just not information that we can get out of the machine learning model. With that, let's actually go back to our slides. Let's talk about some of the pros of machine learning. Machine learning often forecasts noisy and low volume data better than traditional time series methods. This was the case when we looked at the bakery data. When we took a look, we noticed that muffin series were being forecast with machine learning more often than the cake series. If we looked more carefully at that data, we would also notice that the muffin series are a lot noisier than the bakery series. So this is something that we see across a lot of the series that we've tested, that machine learning typically is popping up a lot more and is more useful for noisy and lower volume data. Machine learning allows you to use key sales drivers such as explanatory variables and weather. This is really important, and we saw a good example of that with our minty mouthwash. Machine learning does not require variable selection and specification. Again, we saw in our minty mouthwash example that machine learning is doing some of the variable selection for you. The models are only going to use the variables that are deemed important to the model. Machine learning can automatically account for outliers. And this is somewhat related to our first point about noisy data. It is one of the reasons why machine learning can be very useful for noisy data. Machine learning can automatically handle missing data. This is certainly very useful. It's a big problem in forecasting in general that a lot of models, particularly ARIMA type models, really need to have all of your data there. And then finally, and this is probably the most important of these, machine learning can account for multiple cycles. So if you have daily data, if you have hourly data, if you have every 15-minute data, or even if you have weekly data, you're going to have multiple cycles. What we mean by multiple cycles, so for example, if we think about daily data, you're going to have a within the week cycle, and you're going to have a within the year cycle. If you're only forecasting out a couple of weeks, that might not really matter because the seasonality is not going to change a whole lot in your forecasting horizon. But if you're forecasting out longer, you're likely to want to account for those multiple cycles. Let's actually take a look at an example in Forecast Pro of data that really benefits from Forecast Pro's ability to identify multiple cycles in machine learning. Let's take a look at a little bit more data. And again, this is some new data, and this is actually hourly data. It is inquiry data, so hourly inquiries. Right now, we're just showing the historic data. And one of the things that really stands out is obviously within each day, there is a very strong within day cycle, but we also see a within week cycle with the first 2 days here having many fewer inquiries than the other 5 days. I'm assuming that these are weekends and these are weekdays. You'll also notice that we have a vertical line down here. That's because for this data, what I want to do is compare how well machine learning works for out of sample versus an exponential smoothing model. So the data over here, this historic data, we're going to reserve. And what we're going to do is we're going to compare the forecast generated by the data on the left-hand side to the historic data that we have here. And that's what we're doing when we do out of sample forecasting. So currently we have a machine learning chosen. That's what expert selection selected. And you can actually see if you compare this cumulative MAD here, it actually looks to be drastically better than exponential smoothing. So let's go ahead and add in the forecast. And we can see that in fact, the machine learning out of sample forecast seems to be doing very well. There's not a whole lot of difference between the green and the red lines. So this is a really good forecasting model. Now let's take a look at the alternative, so exponential smoothing. So I'm going to come over here and just use automatic exponential smoothing. And what you can see is when we use exponential smoothing, we're only capturing the within day cycle. We are missing the within week cycle. And on these two, on Saturday and Sunday here, we are drastically overestimating our inquiry demand. You can also see that with Box Jenkins. Box Jenkins, a little bit better, but also not doing a very good job of forecasting. So this really is a good example of how much better machine learning is going to forecast multiple cycle, particularly these very strong multiple cycle series, than some of the more traditional forecasting methods. Now let's take a look at some of the machine learning cons. First up, and quite importantly, machine learning is computationally intensive, so processing time is considerably longer than traditional time series methods. This might be okay if you don't have a whole lot of series in your project, but if you have tens or 50,000s or hundreds of thousands of series in your project, you're going to need to either allocate the time and be patient for the model estimation, or you're going to want to think about maybe turning off machine learning for all series. So disabling machine learning and expert selection, and instead using it only for the series that really need it, or perhaps using it for just one level of your hierarchy. Machine learning focuses on forecasting, not explaining relationships. When you do a regression, you're going to get what we call a coefficient that basically tells you how your sales drivers impact your forecast variable, your demand. Or when we looked at the event model with Mouthwash, we were able to get an event index that told us how much higher sales were when a promotion was running. We don't get that with machine learning. Yes, we can see the relative importance of a feature, but we don't really see the impact of that feature on sales. And that really leads us to this next point, that because it focuses on forecasting and not explaining relationships, it can be hard to understand why a machine learning forecast is what it is. Very often an explanation makes us understand and see why a forecast is what it is. Machine learning is a bit more of a black box. Extreme gradient boosted trees don't extrapolate trends, although we are working on ways that we might be able to integrate trends into our forecast a little bit better. In terms of trends changing, if you're looking at a forecast 3 to 6 months out or even a year out, it's unlikely that the trend is going to have a really big impact in that forecast horizon. So for the most part, this has not been a major problem for those kind of medium-term forecasts. But if you're forecasting out longer, or if you have a very strongly trended series, machine learning is unlikely to work well for you in its current form in Forecast Pro. So, when should I forecast with machine learning? When you have important demand drivers, when you want to integrate domain knowledge into your forecasts. Machine learning can be much easier to work with than something like a regression model because it really handles a lot of that variable selection and model specification. It's much more straightforward to integrate domain knowledge into a machine learning model than it is to a regression model. When your goal is to forecast, not explain the relationships between features and demand. When you have frequent unexplainable spikes or complex patterns in your data. This again goes to one of the pros of machine learning being that it works well with noisy data and it has some built-in outlier detection. When your forecast should fall within the historical range, so it's not very trended. And again, this goes towards one of our cons that currently extreme gradient boosted trees do not handle trends very well. And if it is heavily trended, then again, you probably should think about using more of the traditional time series methods. When you have data with multiple cycles. So we just saw how much better machine learning works with hourly data. And that is also the case for daily data. And typically, even if that data is not noisy, even if it's very regular, if you have that granular data, machine learning very likely is going to do better than traditional time series methods. And simply put, and probably a bit obvious, but when machine learning outperforms other time series methods. So you don't really know how machine learning is going to do until you actually try it. Really, at the end of the day, the best way to decide what model to use for your data is to do some out-of-sample forecasting and compare the various models on your own. And if you find that machine learning helps, then by all means, go ahead and use it. So that concludes this presentation on machine learning and when you can use it and when you should use it, that is. And I hope it has proven very helpful.
All right, thank you, Sarah, for that great presentation. We're going to be getting into the Q&A portion in just a minute. So just a reminder, if you do have questions, put them in that Q&A function down at the bottom of your screen. As you know, today's webinar was brought to you by Supply Chain Business Solutions in partnership with Business Forecast Systems, the makers of Forecast Pro. Supply Chain Business Solutions is based in Sydney, Australia, and they've been a value-added reseller of Forecast Pro since 2000. They're one of the most experienced international resellers of Forecast Pro. And over the last 20 plus years, Supply Chain Business Solutions have had Forecast Pro customers in virtually every country in the Asia Pacific region, as well as some in other parts of the world. So you all heard Dinesh at the beginning of the webinar. Dinesh is from Supply Chain Business Solutions. Don't be afraid to reach out to him. You can contact him using the details here on the screen. And as we mentioned, this webinar is being recorded and it's going to be posted to both our website and the Forecast Pro YouTube channel. As Dinesh mentioned, we'll be emailing you next week when the recording is available. That will also include the slide set. And finally, you saw Sarah use Forecast Pro today. If you're interested in learning more about the software, reach out to us. You can request a live web demo for your team. We can make it really customized, use your own data. We also have a free trial version. You can try out the software. So visit our website at forecastpro.com or give us a call at the number on the screen. Or if you want to, you can scan a picture of this QR code here. It'll take you to a landing page that has information about Forecast Pro and makes it really easy for you to reach out to us for a demo or a trial. So with that, we'll go into the Q&A portion.
And Sabina, you might have to turn on my video for me.
Oh, sorry about that. I'll do that right now. Okay. There you are.
Yes. Okay.
Awesome.
So do we have some questions?
We do. We have a couple questions. And before we get into it, just a reminder, as Dinesh mentioned, if we don't have time to get to your question today during the live session, we'll follow up by email. So don't worry, we'll get to your question. You'll get an answer. I'll start off with the first one on our list. They asked, in your experience, how often are machine learning models more useful than traditional forecasting models when you take into consideration the cost and the timing to set up the data and run the models?
So, like a lot of things in forecasting, it depends. Starting off, in terms of the data setup and setting up the ML models within Forecast Pro, again, kind of taken away that heavy lifting. I think outside of Forecast Pro, so if you're trying to, go, do something in Python or something using like GBM or XGBoost or something like that, it is going to be a lot of time, and it's going to make a lot of sense if you have a lot of data and a lot of different series that are pretty closely related. One of the scenarios in which ML works particularly well is when it's something called global ML. So instead of estimating or forecasting a single time series one at a time, you put all of the time series together and forecast everything. So you're basically pooling it. And if you have series that are closely related and can basically learn from each other, that is often going to make a lot of sense, and it is worth the cost and time to set up that data. Outside, going back to kind of the Forecast Pro scenario, though, those last couple of slides go through, when ML makes sense and when it doesn't. But just to reiterate some of those points, I do think that if you're dealing with very granular data, so, hourly data, more granular than that, or daily data, it's often going to make sense to consider an ML model. If you think about some of the bakery series, though, that we looked at, where it's monthly data, you don't have super long data. Yes, ML was chosen for a lot of those series, maybe about a third of those series. But I think that there is a question of, when it is chosen, is it that much better than a traditional forecasting method? And again, for that series, it's small enough that it doesn't take a whole lot of time to estimate. But if you had a really large project of basically bakery type series, so monthly, not too messy type series, enabling ML actually might have a really big impact on how long it takes. And while it probably would be forecasting a little bit better, I think that there is a real question about, is that extra time worth the relatively small improvement that you might be getting for that, pretty regular monthly data?
Great. We'll go on to the next question. We are officially past the scheduled time. We'll stay on for a few minutes, answer a few more questions. But the next question they asked: can Forecast Pro detect when data has a trend so that it can select a time series method instead of machine learning?
So we did not actually have a rule about trying to detect a trend and then eliminating ML, but because of the way that we evaluate ML versus traditional models, it's going to kind of naturally, you're not going to see Forecast Pro choosing ML for very trended data. And that does come down to the fact that, one of the most important factors in what's chosen is the out of sample tests. So if you have very trended data, then ML is not going to perform well in those out of sample tests. And Forecast Pro is going to choose something like exponential smoothing instead.
Okay. The next question they asked: do machine learning models provide error ranges?
So we do provide error ranges within Forecast Pro. And the officially, ML is not really a statistical technique. So the concept of, when you have a statistical model, you often can mathematically derive what the theoretical error is and have formulas like that. You don't really have that with machine learning and regression trees and things like that. So the way that we address error ranges and being able to put up confidence intervals and so on is basically kind of a bootstrapping type of thing. So what we did is we look at the out of sample test errors. We look at the size of our misses, and we develop a distribution based off of those out of sample errors that are observed in the data.
Okay, great.
Okay.
Well, it looks like I don't want to run too long after. So it looks like that will be all the questions we'll have time for. But again, thank you everyone for joining. Really appreciate you taking the time. And Sarah, Dinesh, I don't know if you want to say goodbye, and thank you as well.
Yeah, of course. Yeah, I enjoy putting together this webinar, and I enjoy the questions. And we really appreciate our partnership with Dinesh, and the fact that he gave us this opportunity to connect with a part of the world that we don't ordinarily get the chance to. So thank you.
Oh, Dinesh, it looks like you're muted. Let me unmute you.
Oh, sorry. Yeah, sorry.
You're good. There you are.
Thank you everyone for attending. We'll loved it, and yeah, look, we'll see. Based on the success of this webinar, we might present a few more webinars in the future. But thank you everyone for attending today. Thank you.
Thank you, everyone. Have a great rest of your day.